Continuing on with populations part one. And you're concerned about populations when there's a population of conservation concern. Oftentimes it is of concern because the population size is low. It's been brought down by habitat loss or poaching, overhunting, overharvest, or habitat degradation in general. And then also populations, especially those that have been fragmented, become isolated. So you have small populations that are isolated from each other, from other populations. So this is many, if not most, conservation problems involve cases of where the organism you're trying to conserve is like that. Why is that a problem, though? Why is small population size a problem? Why is population isolation a problem? Here's an example here of the Florida yew. Now, Florida is a showcase of endangered species, threatened species, and habitat destruction. So it's really concerning the hurricane that hit in the Lee County area here, Hurricane Ian. It obviously it did terrible damage to and was killed a lot of people, destroyed homes. It also wrecked habitat. Now that Florida Peninsula just sticks out there into the Atlantic Ocean, the Gulf on one side, the Atlantic on the other. So, obviously it's a big target, always has been for hurricanes. However, what's not normal is for populations of like the Florida yew to be so small that one hurricane could wipe them out. Same with the key deer. So populations become very small. One little event could wipe them out. It could be disease, or it could be habitat destruction of that last patch. So this is why you're concerned with populations that are small and or isolated. When they're isolated, what it means is that if that isolated population goes regionally extinct, then it can't be recolonized by individuals from the outside because it's isolated. Maybe they're separated by roads or non-habitat. So to get thinking about what I want you, before we move on here to our first our big example we're going to use, which is the red-cockaded woodpecker, I want to just think about what this right here, demographic and environmental stochasticity. Stochasticity is random change. Let's take a look at that. We're going to use an example of the yellow-bellied marmot. So these are what I mean by yellow-bellied marmot. They look a lot like a woodchuck, but they're kind of the woodchucks of the western United States, at least the mountainous regions. This is Greg Florent, who I know, and he studies has for years yellow-bellied marmots, ecophysiology of yellow-bellied marmots. That's what they look like, and they live out in these rocky open areas. They live in colonies, so it'll be mom and the kids and her sisters and their kids, and usually one adult male. And then, so that's how these colonies develop over time. So they're highly social, not unlike our woodchuck here, which is more solitary. And they're really cute. They're really nice. I studied, that's what I did my dissertation on, in habitats that look like that. So they live in colonies, and actually this is a species of not of conservation concern at all. They live out in places. So the place where I worked is actually is here. This video shows the East River Valley in Colorado. This is what it looks like during the winter. And actually, this is there's winter when there wasn't that much snow. A friend of mine lives in that house right there. But anyway, the field station is up there. Here's the field station. All the marmots in Colorado and all the marmots in the West at this point are in hibernation. During the winter, they hibernate for 6 to 8 months of the year. That's Crested Butte back there, this key resort, Crested Butte. And this is the landscape. So it's for, so the marmots, they're hibernating and they have to build up a lot of fat and resources to survive the winter. Otherwise, they turn into little marmot popsicles under the ground and they just basically popsicle mummies, I call them. 40%, at least 40% of all marmots hibernating don't make it. If you look at their colonies, so let's take a look here. Let's go to Crested Butte, Colorado. Is the nearest town to this field station, the Rocky Mountain Biological Laboratory. Go up the valley from there. That's the ski town. That's the tourist town, and the ski town's up here. Ski Mountain right there. You see the ski runs. You come up here a few miles. Here's the field station called Gothic. Is Gothic. People call it Gothic. It's the old mining town. It was formerly called Gothic, but now it's the home of the field station, which is the Rocky Mountain Biological Laboratory, also called RMBL, also known as Rumble. So these colonies, the marmots, you can find marmots, just about anywhere in western Colorado, but they typically are found in colonies, and the colonies are only in certain places. So like, for example, I happen to know of a colony, see if I can find it, right here. So this is a trail called the 403 Trail, really popular mountain biking, hiking trail. And right here, people probably walk by and don't realize this is a famous colony. This colony of marmots has been studied continuously since 1964. Every individual trapped, ear tagged, and followed throughout its life. And so when I was there, there were probably 6 females, their offspring, and then 1 male, and then up there a little higher up here, sometimes there'd be another male up here, and maybe another female there, depending on the year. This is sort of called talus. It's a kind of glacial rubble. And during the summer, this is all lush vegetation. There's plenty for the marmots to eat. For about 4 months of the year, there's plenty to eat for marmots up there, and then they have to build up a lot of fat. So that's the context. There's that colony, and then there's 4 other colonies that have been studied in this valley all around the lab area. So with that context, it was Picnic Colony, what I just showed. That's the picture right there. And actually, since I first did my study in the 1990s, these trees have all come in since then right here. Those trees were not there. So there's the colony there, there's the species. And what does this have to do with demographic and environmental stochasticity? This graph shows us a period from the 1960s to 1990, and just showing fluctuation in population size over time. And since this study was done, it's been 30 years since then, the data have continued, and it's the same thing. So what you're seeing here, these different lines, but first of all, the different boxes here are different colonies. So you have, let's see if I get it zoomed in. Yeah, so here, for example, is Picnic Colony, and you see the number, these are years down here. So 3 different colonies. We'll just focus on Picnic Colony. You can see numbers go up and down over the years. If you're talking about yearlings, juveniles, adult males, and adult females, they vary over time. There, you see there's a period of time where the number of yearlings year to year didn't change much. In other years, they fluctuate. Look at this, there's an increase right there. More recently, we've seen this. I don't work there anymore, but and then after 2000, there was a big increase in the total number of marmots in those colonies. This is all summed over all the colonies. This is especially true for juveniles. So big production of offspring after 2000. And there's actually some hypotheses that in fact that climate change might at least temporarily benefit marmots. That is the warming, relatively slightly warming temperatures year to year, and the mountains might actually benefit the marmots. But here's what I want you to notice: ups and downs. Over the years, populations go up and they go down. Why do they do that? I can tell you personally, from personal experience, one reason why that is because things happen. So there's a colony down here called River Colony right here. And it's pretty funny. The marmots live in holes in these rocks down here. And these are marmot trails you see here. These are actually marmot trails. There's trails actually here on the sort of the cliff face. And every now and then something will happen, like a coyote will come in and eat a bunch of individuals. But one year, this has been like mid-90s, late 1990s, a badger moved in with 2 young. It's a female badger, came in with 2 young, and she ate 1/3 of all the colony over a period of about 3 weeks. So friend there, he was doing his dissertation and he lost a lot of data. I didn't. I was just actually working as a research assistant, and it didn't actually, all I needed was DNA from these marmots, so it didn't actually bother me. But I went down here and this badger, she was down in one of these holes here. You can't see, but she was down in here and with her young, and if you walk by, she'd growl at you from the hole. So she was in a marmot hole. She had eaten the marmot that was in there, and she was down growling, and her young also growled. Anyway, one badger comes along, waddles in, eats a third of the colony, leaves. And then the colony has since come back. And so that's just a random chance thing. A badger comes through, and that rarely happened there. But things happen. Sometimes a black bear, I was setting traps one night up here, a black bear walked right behind me. Neither one of us saw each other until the last minute there. And then you have some winters are harsher than others. They haven't had a harsh winter in a while, but some winters, 1995 was the record. There's over 600 inches of snow. And even on June 1st, there was avalanches coming down the mountains. That was a terrible year for hibernators because the snow was packed so deeply and so tightly well into spring that it took a long time for vegetation to come up. That was a big killer of wildlife that year. So with that context, let's think about stochasticity. First of all, demographic stochasticity. Demographic, here's a definition here, results from chance independent events of individual mortality, live or die, reproduction, do you reproduce or not? You have more males than females, causing random fluctuations in population growth rate, primarily in small populations. So for humans, I can just give you an example of demographic stochasticity, kind of a silly example, but is that my family, the Floyds, especially the Floyd side of my family, for whatever reason, we're 6 grandkids. I'm one of 6 grandkids. If you look at our kids, and now there's grandkids out there, they're almost all girls. Very few boys. Now the grandkids, I'm one of quite a few. Oh, well, there was only one girl. But at this point here, my cousin Walt, my brother Danny, and all the others, what did they have? They had a lot of girls. I don't think there's one boy. That's right, one, maybe 2. There's quite a few grandkids now. For whatever reason, it's a lot of girls. Another example, just completely random example, is among my close friends from that field station. Actually, we've all been friends since that time. For whatever reason, we've all had girls. There are basically literally almost no boys except for one, just one. We had a reunion about 2 years ago. There was one boy and a whole bunch of girls. So that's just random, and that's a silly example. Let's get back to nature or natural example. So a female marmot, for example, might have a litter of 8. And it's possible most of them could be males. And over a period of a year or 2, that colony may produce mostly males, and it does happen. And it's not really clear why that is, other than it seems to be random chance. But that's going to have impacts on the population growth rate. If you have basically too many males or too many females, that's going to cause fluctuation. I just want to bring this up as just an example of demographic randomness, stochasticity. Same thing with do you live or die? Could be just random. Could be just be a function of random events that have nothing to do with the environment around you at all. That would be demographic. So demographic is generally considered to be within the population as opposed to something coming from outside the population and impinging on that population. It's demographic. So females have year-to-year variation of fecundity, that is the number of young they have. Their litter size, for example. How about environmental stochasticity? So environmental is where something comes in from the outside and affects the population from the outside. It's not a function of the population itself, individuals just reproducing and living and dying themselves. So for example, I mentioned a predator could move in, a really big predator could move in. You could have a high population of coyotes in some years. That would be environmental stochasticity. The date of snow melt. So when the marmots come out of hibernation, this is what it looks like. Actually, a little less snow than that, but there's not a lot of green vegetation when they come out. So if that doesn't happen till late in May, that's less food. They get a worse start on the summer. They may not even survive to even move into June and start, the summer. They may not even live to that point. That's an example of environmental stochasticity. And here's a definition. Results from temporary fluctuations in mortality and reproductive rates of all individuals in the population in the same or similar fashion. So everybody's affected by it. There was a wood frogs and imagine drought, the way drought affects wood frogs in North Woods this year and other frogs. So this year there was a big drought, July and August were very dry here. And, everybody, all the species that are affected by drought in North Woods were all affected by drought. Okay. It causes population growth to fluctuate randomly. Why I say random? Because these are random events. Weather, random. Predator pops in, random. So that's random fluctuation. Does it really matter which one's which? No, but these are, but why does this matter? Why does this matter? Because, here's another example of environmental stochasticity or tropical storms. So we just saw Ian that came through and undoubtedly did cause a lot of damage to populations of wildlife. But you look at the big hurricanes a few years ago, like Maria, that hit Puerto Rico, and it devastated forests there and really could have wiped out the Puerto Rican parrot population, except they had they brought some of them into captivity. And so the population did survive that. That's an example of environmental stochasticity. A hurricane, Puerto Rico is pretty small. Chances of getting a direct hit from a Category 5 hurricane are really slim. So it's a stochastic chance. So we will, at this point here, I'm going to stop because we're going to look at, we're going to introduce a study system called, which is a species of woodpecker, a bird called the red-cockaded woodpecker. We're going to use this as an example because it's an endangered species. It's been reduced to small population sizes, which are fairly isolated populations in the Southeast United States. And so they are vulnerable to demographic environmental stochasticity. So here's the deal. Your small populations, the things we were just talking about with marmots, none of that. See, nobody's concerned about marmots because their populations are large and they're not endangered. Puerto Rican parrot populations are small. So when there's random fluctuation in their population sizes, from demographic stochasticity or environmental stochasticity, that pushes them close to extinction. As you've already small population to begin with, it's closer to extinction. It can be pushed into extinction more easily than a large population. And that is the case for the red-cockaded woodpecker, which will be introduced in the next video.